Welcome to my channel, STEM Cafe, where we make everything science, technology, engineering, and mathematics something you easily comprehend, assimilate, have as fun, enjoy, easy to record. We make sure all these things are very interesting and fun. Today we continue with forces. We have talked about forces as push or pull. Push or pull. And we have said that forces, what do? They change position, they change structure. Today, we are dealing with addition of forces. Addition of forces. We continue with that. Addition of forces. When we are given forces, we always be given direction. And when the directions are not on the same line or parallel, that is, they are not in the same direction, either opposite or facing the same direction, the addition will not be easy like algebraic. We have to add them as we add vectors. That's how we add the forces. So forces are added as any vector, as vectors. Now, I will look at 3 or 4 ways we add forces. Let's start with where we have just 2 forces. Addition of 2 forces on particles. On particles. Please, I want you to take note of this. In STEM, we take body sizes very serious. When the sizes are negligible, when the sizes are small, or negligible, we can go on to just add the forces. So, we refer to the body as particle. So, instead, when we are handling situation, and we don't want to consider the sizes, the dimension of the body, we just look at it as particles. Sometimes you might even look at the body as big as truck, as particle. So you just say like, size is not to be considered in this situation. So that's the way. Or we just tell you, view it as a particle. But when the sizes are important, we talk about rigid bodies. This is where we talk about particles. A body composing of several particles, but the distance of the particles from one another is constant. Contains several particles, but the size and shape is constant. Why? Because the distance of the particles from one another remains constant. So we get to that one too. But for now, let's look at addition of forces in particles. I am going into addition of 2 forces. The techniques we look at are 1. We use parallelogram law. 2. Triangle. 3. Resolution of vector. Resolution of the forces. And when you do this resolution of the forces, you can go on breaking it algebraically into two perpendicular components. You can break into two perpendicular components, or you express it as vector. It can be two depending, it can be three, it can be two. Or expressing them into vectorial expression or notation. When you know this, you will see anything is there as form. Let's start. Let's look at the parallelogram one. Parallelogram. Please understand this before you start thinking of, oh, let us use it to work examples out. Understand it so that I can apply it even in situations that I cannot bring up. Let us say we have forces like this. This is theta 1, F1. Theta 2, F2. Let's now try to use parallelogram law to find the resultants. That is the sum of the two. The first thing is how your base is here. This is F1, theta 1, F2, theta 2. So they can be of any sizes. The direction can be anyhow. Since you have drawn these two, you will now complete the parallelogram by drawing parallel sides to each of these forces. And this one. So this place is equal to F1 and this place is equal to F2. So you have it like this. You can see from the intersection here, draw a diagonal to meet this point. So this is the sum. We always refer to the sum of two vectors as resultants. The sum of two or more vectors as resultants. That is the force that we add. The total combination of these two. Now this will be the direction of the resultants to the horizontal. You can see. So it's very easy when you use parallelogram law. Once you have drawn it, you can draw it to scale using your ruler and other drawing instruments. Or you can draw like this and then use analytical process. If you draw to scale, all you need to do is to measure. And then you do every other thing. You draw the angles. So you use your ruler to measure from here to here. And your protractor to measure the angle. You get the answer. So you can do that. Now let's look at the triangle. If you use the triangle, it is very much the same like the parallelogram. Let's see how that works. Now let's see if we use triangle method. The same thing like the parallelogram. This is our horizontal. Let's draw our F1. F1, theta 1. Can you see? Now, you now take from the end of this arrow of F1, draw a force parallel to this line with the same size. Let's see. So you can see, this is my theta 2. You can see, I have drawn it parallel to this one. Now, the resultants will be like this. You can see. Same thing. If I had drawn it complete, it will be like the parallelogram. You can see. So, and this will be the direction of the resultants. You can see. Very simple and straightforward. You can do the analytical or draw to scale and measure. That's how you do that one. The third one. Now, look at this. You have to resolve the forces into their components. Like this one now. have this. Look at it. This is very good for me. This one goes up, right? We say this one is positive and this one is positive. Just as our Cartesian. The one that goes down, negative. And the one that goes left, negative. You can see. So, for me to resolve this one into its components, what do? I say, I break into components. Let's make this one x, y. So f1, if I want to get the component of f1 along the x direction. Now, let's resolve the forces into components. So for f1, we have f1 cos theta 1 along the x direction, horizontal direction. Along the vertical direction, we have f1 sin theta 1. You can see positive. Now let's look at f2. We have f2 cos theta 2 because it is in the positive direction. Now look at it now. It's downward. You have minus f2 sin theta 2. Now you now have r. The summation of this rx. The summation of this ry. So r will stand like this now. You can see. This will be the ry, this will be the rx, and this will be the r. So magnitude of r will be square root of rx squared plus ry squared. You can see. Then what will be the direction? It will be direction theta. This one. It will be equal to ry arctan ry over rx. That is the direction of the resultants. And this resolution of forces, I said that you can express the forces in vector notation and then you add. Look at this. F1 will be f1x plus f1y. So f1xi, f1yj. And what is our f1x? It will be f1 cos theta 1i plus f1 cos sin theta 1j. Sin theta 1j. For f2, we express it in this vector format. It's going to be f2 cos theta 2i minus f2 sin theta 2j. You can see. Please refer to the lecture on scalars and vectors. You get it far better. And then from here, when you are adding, it will just be r will be equal to summation f1. It will be f1 plus f2. And by the time you add it, you realize that it will be f1 cos theta 1 plus f2 cos theta 2 I plus f2 sin theta 2 minus f1 sin theta 1 minus f2 sin theta 2 j. So you can see this will be the horizontal component, this will be the vertical component, and from there you get the magnitude and direction. That's how we treat the addition of two forces. As I promised, I said I want to say something about resolving forces for addition, two forces for addition, just to make that polygon clearer. I have done it, but I still want to show you. Let's say this is theta 1 f1 and theta 2 f2. Now, let's resolve these forces. It will be like this. F1 H is theta 1 sin theta 1 f1 cos theta 1. If you look at this f2 now, you have minus f2 sin theta 2 And this one here is F2 cos theta 2. Now let's draw it using triangle or parallelogram. Let's use triangle. This one comes like this. Theta 1, F1, and theta 2, F2. So this will be the resultant. Let's check the horizontal components. And this one. You can see for this resultant, the horizontal component of the resultant will be this place is F1 sin theta 1. This place is F2 cos theta 1. F1 cos theta 1. This place F2 cos theta 2. So which means that the total horizontal component now, you can see, is going, this place is equal to this place. So Rx is equal to F1 cos theta 1 plus F2 cos theta 2. Now let's look at the vertical components. For y now, this place, can you see? F1 sin theta 1. And this place is F2 sin theta 2. So this place to this place, what is it going to be? It's going to be F1 sin theta 1 minus F2 sin theta 2. Can you see from here now? So R1 is equal to F1 sin theta 1 minus F2 sin theta 2. That's what I said I wanted to show you. So you can see the resolution of vector makes it easy and fun. I have also shown you this aspect in the addition of three or more forces. Now, if F1 and F2 are in the same direction, it's in this direction, and F2, let's say theta, and F2 is also in this direction, you can see that the sum R is just equal to F1 plus F2 in that direction. So if it is in the same direction, you can add the forces algebraically. Or if it is directly in the opposite direction. So if it's directly in the opposite direction, this one goes like this one goes like this. F1, F2. You can see this one is theta and this one is theta here. So in this instance, R will be equal to F1 minus F2. And the direction remains the same. Please. So that is for that. Now let's look into summation of three or more forces. When we have three or more forces, I will illustrate like this. This F1, theta 1, F2, theta 2. And this is theta 3, F3. So you can extrapolate it to as many forces as possible. Then, okay, let me do this. Theta 4, F4. You will get something now. Maybe I go back to that later concerning two forces. In this place now, I can just do it like I am adding them in pairs. Let's say I want to add algebraically 1 plus 2 plus 3 plus 4. I want to find, let me say, okay, I can do it like this. 1 plus 2. That's what will give me 3. So to get k, I will still do something like 3 plus 3 plus 4. You can see. Again, I can take 2 again. 3 plus 3. That will give me 6. So 6 plus 4 will equal to k. At the end of the day, 6 plus 4 is equal to 10, which is equal to k. So in this way too, that is what we consider to do this one. But you know we are STEM. We cannot be doing things like this. We do it straight, professionally, with ingenuity. So it's 10 calculate. We just work it straight, and then we get our answer as 10. Now, let us use triangle method, taking them in turns. Let me start with F1. Let me start with F1. Okay, let me go to that. So F1 comes down, theta 1, F1. So yes, for visibility. F1 comes like this. To add F2, I will do something like this. And then this is F2. And this is F2. You can see. Let's say this is the size. Let's now continue. We have F3. For me to get F3, I will draw something like this. And then, sorry, this is the resultant of F1 and F2. Can you see? R1. From here now, I will draw this. F3. Theta 3. So, I need to add R1 to F3. You can see. So this gives me R2. Now, from here, I have F4 again. You can see. How did I get the F4? Theta 4. This F4. So, you can see now, from this one and this one, this is the R3, which is the total resultant of all the four forces. Now, let's break it down. The easiest method I use is resolution of forces. Look at this one. Look at F1. This one now has translated to polygon of forces. Polygon of forces. It has translated to polygon of forces. And what happens now? You can see. This is F1x, F1y, sorry. This is F1x. You can see. This one, you can see this one is down, negative. It is minus. This one goes up. F2y is positive. F2x is positive. So you can see, that's what I wanted to say before concerning two forces. Just this one. You can see that the remnant, this is F, this one is still downwards. You can see the difference now. So it's going to give me F2y minus F1y. You can see. But in this direction, you have F1x plus F2x. You can see that one for me now. Then, let's look at, this is F4. Let us look at this one too now. In this place is F3y. And this place is minus F4y. I just put in this sign for you to know the direction. Normally, I would have written F4y, but because of the I'm just using this sign to show the direction. So it's negative. Look at this one now. F3y minus F4y. You can see how everything ends. This is it. To this place. You can see. So, what I'm trying to show is this, that along the vertical, all you need to do is to add the vertical component. Along the horizontal, add the horizontal component. If you look at F3 now, this one is negative, F3x. For F4 minus F4x. You can see. So along the horizontal direction, these ones are positive, these ones are negative. Along the vertical direction, these ones are positive, these ones are negative. All you need to do is to, for this R now, R will be summation of Fx I plus summation of Fyj. That is after you have resolved each of them. Let's see what it will be like. F1, F2, F3, F4. And the summation will be R. X direction, Y direction, or you can say Ij. So F1 will be minus F1. No, this one is F1 cos theta 1. F2 cos theta 2. F3 minus cos theta 3. This one minus F4 cos theta 4. But if you look at this one now, vertically, for F1 we have minus F1 sin theta 1. This one is F2 sin theta 2. Here, F3 is positive sin theta 3 minus F4 sin theta 4. So this one, the summation of this will give you Rs, and the summation of this one will give you Ry. So at the end of the day, your R is going to be this, like this. So this will be Ry, and this will be the Rx. So the direction will be R tan Ry over Rx. That's all. And if you use normal vector notation, we just break this one to be F1 is F1 cos theta I plus minus F1 sin theta I. So F1 will be F1 cos theta 1 minus F1 sin theta 1. Same thing will be for F2. F2 cos theta 2 plus F2 sin theta 2. F3 minus F3 cos theta 3 plus F3 sin theta 3. So please, this one we have I, this one we have J. I, J, I, J. So F4 too will be equal to minus F4 cos theta 4I minus F4 sin theta 4J. So the resultant will just be adding the I component and the J component, which is the same thing as what you have done. But you can also draw to scale and then measure using your ruler and your protractor to get the answer. Very good, very enjoying and fun. So from here, our polygon of forces. Now let's look at a situation, another interesting situation in addition of forces. That is the situation of equilibrium. A body is said to be in equilibrium when it is at rest or moving with constant velocity. When it is moving with constant velocity, either linear or rotational. Linear or rotational. So in short, we are saying that when the total force, when there is no acceleration, that is when there is no acceleration or deceleration. In this place, we are saying that Newton's first law of motion is observed. That's what we are saying. And this can only happen when the total force is 0. Like Newton said, when there is no external force applied. So this occurs when total force or resultant force is 0 for a particle, or resultant force and moment is 0 for rigid body. Please take notes. For particle, force needs to be 0. But for rigid body, the resultant force and momentum must be equal to 0. We'll get to that one later on, very soon. So, let us now look at some important words in this case. Now, let's look at the important words. We have talked about resultant force before, and we have demonstrated it. The resultant force is obtained by placing their representation, that is the force representation, tail to head in order, and is the single force which, acting alone, will have the same effect in magnitude and direction as two or more forces acting together. That is, when all these forces act together, they will have certain effects, and that force that can provide that effect that all these forces are having upon an object or anything is the force we call resultant. But now we are talking about equilibrium, and that brings us to equilibriant. Equilibriant is that single force. You can see equilibriant and resultant force, they are single forces which will balance all other forces taken together. It is equal in magnitude but opposite in direction to resultant. Now, what do we mean? When all these forces act, we are saying that if we remove them and we replace them with one single force called resultant, it will have the same effect as all of them. And now we are now saying, if all these forces act and there is one resisting force that will nullify their effects, that is what we call equilibriant. So if you look at it, if resultant is like this, and another force that can come and nullify it, we call this one equilibriant, and this one resultant. So at the end of the day, summation of resultant plus equilibriant will give us 0. You can see resultant plus equilibriant will give us 0. Therefore, resultant is equal to minus equilibriant. So what does that show us? It shows that they are both in the same direction, but they are both in the same line. They are in the same line but opposite direction. So that is what it means. They have equal magnitude, act in the same line, that is collinear. Or parallel. And yes, but opposite in direction. So that is it. The most important thing is know that they are equal in magnitude but opposite in direction. That's all. So if I have three or more forces acting in a place, and I am asked to find the resultant will be the force that will cause it to become 0. Let's just look at it algebraically. When we are trying to show what resultant means, we brought expression like this. And this is R. We got 10. But what we are now saying is that equilibriant will be something like this. That is, it will nullify the effect of all these forces. Just like two of you pushing yourselves. Okay, let's say I have 3 people pushing me, or 2 people pushing me. Their forces have resultant. But if they cannot move me away from where I am, it means I am giving equilibriant to their total forces. So This one shows that E is equal to minus 10. Like this is what I'm. Now let's look at this box now. Let's say F1 acts like this. F2 acts like this. Now, the resultant will be like this. So, the total forces, that is, this body will have the same effect as if these two forces act on it. When you apply this R in the direction, that is it. So that is what resultant is. But now let's leave F1 and F2 on it. You know, it will move this body. Let's say that's N. And you know, R will move like this. You now bring a body, you now allow a body with force of magnitude R. We call that one equilibriant. And it moves like this. You will realize that this body, the velocity, as in the acceleration, will become 0. So it will be in equilibrium. So that is, you can see, E acts opposite to R. And that is what equilibriant just means. So if you are adding 2 or 3 or 4 forces, you have, let's say you have it like this, like the one we had before. 1, 2, 3, 4. You know, we said this will be our R. Are you getting it? But equilibriant will be that one that will bring it to 0. So from here to here will be equilibriant. From here to here now will be the resultant. I hope you see it very clearly. For that one we did the other time. This is F1, F2, F3, F4. You know, from here to here is the resultant. You can see the direction of the resultant is from the tail back to the stick. Can you see? But the force that will bring everything to become 0, that is the equilibriant. So from here now to this place is the equilibriant. Please, I want you to understand it very well. Nothing is simple. Resultant acts like this. Equilibriant acts opposite it, and it makes it 0. That's all. And it makes it 0. Now let's talk about equilibrium of 3 forces. Equilibrium of 3 forces. Please, I think I have made it clear that if we have 2 forces that are in equilibrium, it means that the first force and the second force are equal. If 2 forces are in equilibrium, it means F1 equals to minus F2. That is, F1 and F2 are having the same magnitude and acting the same line but opposite direction. That's all. Nothing to disturb ourselves about. Therefore, F1 plus F2 equals 0. They are parallel to each other. But now we are talking about 3 forces. When we are having 3 forces in parallel and in equilibrium, 3 forces in equilibrium, it means that they are either parallel to one another, and the sum of 2 cancels one off. But in this instance, we are talking about the situation where they are not parallel. The situation where they are not. So, that is, the forces are not collinear. They are not on the same line. We can now draw like this. Let's see. F1, theta 1, F2, theta 2, and let's see, F3, theta 3. You can see, they are not parallel, nothing. So, if we want to draw this one, what will happen? Let me start from F1 like I did before. Don't forget, it is in equilibrium, so the mouth must close. So I start like this. F1, theta 1. From there, F2, theta 2. And now, this is F3 please. It was come down like this. because the mouth must close. Are you getting it? So what does that mean? It means that the three forces acting at this point, if they are in equilibrium, we can represent them as the three sides of a triangle. We can represent them as the three sides of a triangle. So at the end of the day, we can use any triangle ratio or any analytical method to get any side of triangle, to get either the size of the force or the direction. So let's look at it again. You can also see it like this now. You can see we have theta 1, F1, theta 2, F2, theta 3, F3. If you look at it now, you can see that they are in equilibrium. Let us say, like I explained the other time, F1 and F2, let's sum it together. By the time you sum F1 and F2 together, it must give you something like this. Now this is theta 2, theta 1. So we are going to have something like this. F3, theta 3. So we have summation F1, F2. And this is F3. So this is E to 3. R for F1, F2. Summation of F1, F2 is going to be equilibriant for F3. So you can see this place will also be theta 3 as this one. So that is what the sum here will give. Take note of that, please. At the same time, when you look at this, by the time you sum Fx, it will be equal to Fy, and it will be equal to 0. You can see. So, depending on the situation you fall into, you can easily maneuver your way out. I have shown you this condition now, I have shown you this condition now, and I have shown you the one that shows that you can represent them by the sides of triangle and the angles. You can see. So, let's now talk about triangle of forces now. So, this one now leads us to triangle of the forces. So now, this is about triangle of forces for equilibrium of three forces. Triangle of forces. So it states that if three forces acting at a point are in equilibrium, then they can be represented in magnitude and direction by the three sides of a triangle taken in order. I have explained that one by this. We can also say if three forces acting at a point can be represented by the three sides of the triangle in order, then they are in equilibrium. So we are saying it in another way. So if somebody can draw a triangle like this for you and say, okay, this is for three forces, and ask you a question about them, they are in equilibrium. You get it now? So that's what this is trying to say. So at the end of the day, we can conclude that if three forces are in equilibrium, they are either parallel, they can be parallel to one another, or concurrent. You know what concurrent means from our straight line geometry? That is, acts at a point. That is, by the time you draw them, they will meet at a point. So that is what's the basic thing to know about three forces. If it is 42, now, from the three forces in equilibrium, Lami's theorem is a version of sine rule used for analysis of three forces in equilibrium. It is useful when you can get the three angles. So if you know two angles, you can know the third one, since the total angle is 360. Now let's see how Lami's theorem can be used now. I want to get this. Let's start with F1. You know, have F1 up like this. You understand? So I get between F1 and F2. Between F1 and F2, I have this. This is alpha. This, I believe you are getting it. Alpha. So this place is 180 minus alpha. That one is clear. Now between this one, F2 and F3, I have beta. So this one goes like this. So this place is beta. Please, I believe you are getting it. You draw it. So this one is beta. So this place is now 180 minus beta. This is F2. And this one is F3. And like we said, you draw the sides parallel and the angles also must align. So what does that mean now? The angle between F1 and F3 is this. This angle is theta. So this is 180 minus theta. And if you look at sine rule, it is that this side over sine of the angle it is facing is equal in all sides. That is F1 over sine 180 minus beta. That is this angle. F1 over sine 180 minus beta is equal to F2 over 180 minus theta is equal to F3 over 180 minus alpha. Wait, sine, please. Sine. Please. Sine 180 minus theta minus. And if you know from our angles in all this in different radians, we know that sine is positive here, sine is positive here, and this place is for 180 minus theta. Therefore, sine 180 minus beta is equal to sine beta. We know this one from our ratios. Therefore, F1 over sine beta is equal to F2 over sine theta is equal to F3 over sine alpha. And if you look at that, F1, this is the angle at the opposite side. F2, this is the angle at the opposite side. F3, this is the angle at the opposite side. So once you have three forces in this format, you have no problem already. Just go straight and work it out like this. You get your answer. Just go straight and work it out like this. You get your answer. So this is the basic, comprehensive introduction of forces. And with what we have done now, you can undo anything. Just try to get these basic aspects. You will get everything you need to get in any STEM subject that requires forces. For more than 3 forces. If it is for more than 3 forces, you are going to have something we call closed polygon of forces. That is, at the end of the day, by the time you draw it, there won't be any space for resultant. It will be closed. Like if you have it like this, everything must close. At the end of the day, it will be closed polygon. That is what we are going to have. And when I have 3 forces, or more than 3 forces, I always like to use resolution or vector notation. Or vector representation. Let me put it like that. So it makes it easy for me to add and to get my answer with ease, just using tables. But if I'm going to draw, I have to draw to scale and all this stuff. That's all about equilibrium of forces for now. So with this equilibrium of forces, we can go to another aspect referred to as moments of forces.